Hello, Upper Six. We've come to the last part of the topic on stars, and basically what I'm going to go through today is putting the physics together, which we've learned so far about stars, such as measuring their brightness and their temperature. And we're going to look at the patterns that link different stars together. And from that, we're going to talk about the physical processes that underlie what's going on in stars, what provides the energy source for stars, and how are stars born, how do they live their lives, and how do they die. So we're going to look at the evolution and life cycle of stars. And we're also going to look at the end product of a star's life, so white dwarfs, neutron stars, and black holes. So it's quite a big topic. So there's quite a bit to go through. As usual, I'll give you this little talk on video. There'll be some notes and some questions to do. So where were we from the end of last lesson? Well, we'd already talked about measuring the brightness of stars, or their absolute magnitude, which can give us the total amount of energy that a star radiates into space. And we've also talked about measuring the surface temperature of a star from the spectra of a star. So those are two important bits of physics that we can measure for stars. Putting them together, by the way, you can also get the radius of stars. You can get the size of stars, which is not something that you can measure directly because stars are too far away, but you can infer it using the black body radiation laws. So we can learn quite a lot about stars from our Earth-based instruments. And one thing that it does tell us is that there's a wide variety of stars. I showed you that little video in the last lesson of comparing the sizes of stars. And you could see in that video there was huge differences between the temperatures and colours of stars and also the sizes of stars. In fact, in that video, you went from the sun up to the largest stars, but it didn't show you stars that were smaller than the sun. So if you've got a variety of objects that have lots of different properties and you want to somehow look at the patterns of these properties, what do? Well, think about other examples of where people had a variety of objects and they didn't really understand the underlying processes. Mendeleev in the 19th century with the chemical elements, he looked for patterns in the chemical elements. What he did was he made a table which organized the chemical elements according to their atomic numbers and their chemical properties. And he saw patterns there. Of course, that's the periodic table. And from that, later on, other scientists were able to infer things like the electronic structure of atoms, which at the time, obviously, Mendeleev didn't understand. It was the electron hadn't been discovered yet. So by grouping objects according to patterns that you see, you can actually learn a lot about the underlying physics of what's going on. Another example of that would be the hadrons. If you remember back in the lower six, we looked at the meson diagrams, which Murray Gell-Mann first produced in the early 1960s. So he plotted strangeness against charge for the family of mesons. Also did it for baryons as well. So all the hadrons. And from the patterns that emerged from that, he was able to infer the existence of quarks. So how can we do something similar to stars? We've got all these objects which all have different brightnesses and different temperatures. Well, the first thing that you could do is draw a graph and plot on one axis, let's say the x-axis, the surface temperature of the star, or the spectral class of the star. It's the same thing. Spectral class, surface temperature tells you the same thing. And on the y-axis, you could plot the luminosity of the star, so how much energy is being given out by the star, or the absolute magnitude, which is, again, the same thing, but on a logarithmic scale. That's exactly what two scientists did, Hertzsprung and Russell, early on in the 20th century. They took hundreds and hundreds of stars that had their spectra measured, that had their absolute magnitude measured, and they plotted them on a diagram with absolute magnitude on the y-axis, so brightness on the y-axis, and spectral class or temperature on the x-axis. And the result of that is called the Hertzsprung-Russell diagram. And if you like, it's the periodic table for stars, or the eightfold way pattern for stars. It's the basis of us understanding what the physics that's going on behind stars is. So you'll see copies of the Hertzsprung-Russell diagram in all of the textbooks. I've got a copy here which I'll show you and talk through it with you. So this is it here. Let me just stand up so you can see it. Okay, so that is the Hertzsprung-Russell diagram, and I appreciate it does look a little bit complicated, but really it shouldn't be. Each cross on here represents an individual star that we've plotted. So on the y-axis, we've got absolute magnitude, and it goes up from a large positive number, which is a very dim star, so stars down here are very dim, up to a very high negative number. So stars along the top row here are very bright. So really this y-axis is a scale of brightness from very dim stars that are not giving out very much energy per second, up to incredibly bright stars. Now remember, magnitude is a logarithmic scale, and each step of 5 magnitudes is actually a step of 100 in luminosity. So actually this is covering a huge range of brightnesses. I mean, if we start here at magnitude plus 15, plus 10 is going to be 10 times brighter than plus 15. Plus 5 is going to be 10,000 times brighter. 0 is going to be 1,000,000 times brighter. Minus 5 would be 100 million. And minus 10 would be 10,000 million, so 10 billion times brighter than the star that's down here. So it's actually covering a huge range of brightnesses because it's a logarithmic scale. And on the x-axis, you've got temperature. Now, confusingly, the traditional way to plot the Hertzsprung-Russell diagram is actually to put the hottest temperatures on the left-hand side and the coolest temperatures on the right-hand side. So kind of counterintuitive, the opposite way round that you would normally plot a graph. And you could also put the spectral classes along the bottom as well. In fact, traditionally that it is plotted with spectral class rather than temperature along the bottom, but of course it means the same thing. So here we've got O, B, A, F, G, K and M. So the coolest, reddest stars along here, and the hottest, bluest stars along here. So you could also think of this as a scale of colour. So blue through white, through yellow, orange, and then red at the end. So different temperatures along the bottom, from hot to cool, and different overall brightnesses along the y-axis, from dim stars up to incredibly bright luminous stars. So when stars were plotted on these axes, what did you see? Well, first of all, the sun, just out of interest, the sun occupies a position fairly central, sort of illustrating its nature as a very sort of dull, uninteresting, ordinary, average star. Probably a good thing from our point of view. But the sun is right there in the middle. The first thing that you notice is that most stars actually lie along a band that's very well defined. The vast majority of stars lie along a band that starts down here at the very dim, low luminosity, low temperature end, and runs in this slightly S-shaped curve up to the top left position on the graph. Now the top left is very bright and very hot stars. And the vast majority of stars lie along this band. Well over, I think about 99% of stars lie in this band here, including the sun. And we call this band of stars the main sequence. Now the fact that they all lie in a very well defined line like this suggests that there is a very similar underlying physical process which is powering their luminosity, which is producing the energy which keeps these stars shining. We now know exactly what that power source is. Every star that lies on the main sequence is fusing in its core hydrogen into helium. Now, the actual reaction itself, nuclear fusion, we discussed it before when we did nuclear physics. It's also called the proton-proton cycle. You basically take 6 protons or 6 hydrogen nuclei and merge them together into a helium nuclei. And then 2 protons are also released and go back into the reaction. So really it's 4 hydrogens turn into 1 helium. And that happens in the cores of all of these main sequence stars. And it's what keeps stars like the sun powered. It's what keeps stars going. How do these reactions start? Well, the origins of a star lie in clouds of gas and dust, mainly hydrogen and helium gas. And we call a cloud of gas in space, we call it a nebula. Now, a nebula, if it becomes slightly denser than its surroundings, will collapse because of gravity. There are various reasons why it might become slightly denser. There could be a passing star, there could be a shock wave passing through it because of a supernova explosion nearby. But if you've got a nebula, a cloud of gas and dust, if it gets slightly denser than its surroundings, gravity will start forming an instability and will collapse that part of the nebula until it gets denser, and then it'll start sucking in more and more material. So you get a sort of runaway effect, a gravitational collapse. And as the nebula collapses, the core of the nebula will get hotter. Okay, gravitational potential energy gets turned into heat energy, well, kinetic energy and then heat energy as the stuff falling in gets closer and closer to the center. So the center gets hotter and it gets denser until you reach the point where the center of the nebula is so hot that the hydrogen nuclei bouncing around, which are just protons, of course, bouncing around, will overcome their electromagnetic repulsion and will start fusing to form helium. And when they do so, well, you know the score because we did it in nuclear physics. You get a change in the mass, which releases a lot of energy, and that's the process of nuclear fusion. And then a star's born. So basically, once the star has collapsed, or once the protostar, the nebula, has collapsed, you will end up with a main sequence star, and you'll end up with a point along this line here. Now, exactly where you go along this line here will depend on the mass of the newborn star. If you have a very low mass object, then it will end up down here. Okay, and actually you can see the way I've plotted it, most stars are actually at this end, and they're much more common than, say, the sun. So something with, say, 1/10 of the mass of the sun will end up somewhere down here. Okay, now not surprisingly, such a low mass star will burn with a very low luminosity because you haven't got that much gravity compressing the core of the star, and it will last for a very long time, and it won't be particularly hot at the surface. So down here you've got very cool red low mass stars that are not producing very much light at all. In fact, the sun's closest neighbour, Proxima Centauri, we can't even see it with the naked eye, and that's one of these stars sitting down here on the Hertzsprung-Russell diagram. As you go up the main sequence, you're also increasing in mass. So stars that are born with more mass, obviously any star that's born with about 1 solar mass will end up somewhere close to where the sun is there on the main sequence. As you go higher and higher and higher up the main sequence, you go to the higher mass stars. So the stars that are all the way up here are 50, going up to maybe 100 times the sun's mass. There is a physical limit on how big a star you can actually produce, and it's about 100 times the mass of the sun. Any bigger than that and it'll just basically explode as soon as it's formed. So there is a limit at this end, and obviously these stars here are extremely hot, Okay, you can see the temperature down here getting up towards 30, 40,000 degrees, and they're extremely luminous. I mean, up here is going up towards about 1,000,000 times as bright as the sun. These stars are also incredibly rare as well. So where you sit on the main sequence does depend on your initial mass. But what they all have in common is that they all are fusing hydrogen into helium in their core. Obviously, these stars up here that are shining with about 1,000,000 times the brightness of the sun, they're not going to last for very long because they're burning their hydrogen so quickly, they're going to run out of hydrogen. Whereas these ones down here pretty much last for trillions of years before they run out of hydrogen. The sun has a lifetime of about 10 billion years, and we're about halfway through it at the moment. Okay, so that's main sequence stars. So the vast majority of stars that you see in the sky are main sequence stars. They're like the sun. Some of them are a bit more massive, some of them are a bit less massive, but they're burning hydrogen into helium in their core, and they can remain stable for a very long time. They're producing energy, which is mostly escaping through the star in the form of electromagnetic radiation. That exerts a pressure on the outside of the star. It's called radiation pressure. And that pressure that's exerted on the outside of the star will stop the star from collapsing further. So you get what's called a hydrostatic equilibrium. So the star is in balance. It's kept at exactly the same size, and the core of the star stays at the same temperature. It doesn't collapse any further, and the reaction of hydrogen into helium keeps the star powered until you start running out of hydrogen. And that's where the other stars come in that are plotted on this diagram. The vast majority of stars you can see are on the main sequence, but you can also see that to the top right of the main sequence, there's a scattering of other stars. Far fewer than on the main sequence, but there's a definite scattering of stars that are in this part of the Hertzsprung-Russell diagram. Now, think about it. If they're to the top right of the main sequence, these are stars that are much cooler, but much more luminous than main sequence stars. Okay, above the main sequence means more luminous, and to the right of the main sequence means cooler. So anything that's in that part of the diagram is cooler but more luminous. Now, anything that's cooler and more luminous, if you think about the black body radiation laws, to have more luminosity but not be as hot, you must have a much greater surface area. So these stars are all huge. They're bigger, much bigger than main sequence stars. And in fact, the further you are in that direction, the bigger the stars get. The one I've plotted there is probably Betelgeuse, which is a red supergiant star. And if you were to put it in the solar system where the sun is, it would stretch out as far as Jupiter. It would completely envelop the inner planets. So these stars up here are really, really huge. They have an enormous radius, but they're also, if they're that far over on this side of the Hertzsprung-Russell diagram, they're also rather cool as well, their surface temperature. So clearly something physically different is going on from the main sequence with these stars here. So what exactly do we think has happened to these stars? Well, these are stars that have already been through the main sequence. So unlike the sun, they have been through the main sequence and they have finished their their phase of burning hydrogen into helium. Now, at some point, the amount of hydrogen in the core of the star will drop to the point at which you can't sustain a reaction of fusing hydrogen into helium. And two changes happen to the star at that point. The hydrogen burning, or the hydrogen fusing, will move to a shell that's further out in the star, outside the core. But the core, because it can no longer support itself, will collapse. And it'll collapse and become hotter and denser. And as it collapses and becomes hotter and denser, at some point, helium, which was the byproduct of fusing hydrogen, will start to fuse itself into carbon and oxygen, so obviously heavier elements in the periodic table. And when that happens, that releases a huge amount of energy. The reaction to convert helium into carbon and oxygen produces a lot more energy than hydrogen into helium. And at this point, the star moves off the main sequence. It becomes a red giant, and it produces a huge amount of energy, which pushes the outer envelope of the star outwards because you're out of balance now. The radiation pressure with gravity, so the outer envelope of the star expands. Rather counterintuitively, the outer layers of the star will cool down. Now, that's not because you're producing less energy, you're actually producing a lot more energy from the core. It's just that because the outer layers of the star have expanded, remember the Stefan's law, luminosity equals constant times area times temperature to the power fourth. If the area is increased, then the temperature must drop. So the outer layers actually become cooler, but overall you're still giving out a lot more energy. So that's why they tend to become redder. Okay, so a star will evolve off the main sequence. And in fact, what I've shown there is the evolutionary path of the sun over the next 5 billion years or so. Now, at the moment, the sun's on the main sequence and it's not really moving. In the next billion or 2 billion years, it may move slightly up the main sequence, okay, but it's not moving particularly far. It'll get a little bit hotter and a little bit brighter. But then in about 5 billion years' time, the hydrogen fusion will switch off, and the helium fusion will switch on. And it will follow a path which takes it into the red giants, and the sun will swell out to a huge size. It'll envelop the inner planets, Mercury and Venus. It will probably just about get to the outer layers of the sun, will reach where the Earth is now. If the Earth survives, it will all the oceans will be boiled off into space, and the only thing that will be left will be probably the core of the Earth. But that's the fate of the sun. I wouldn't worry about it. It's 5 billion years' time, classed as somebody else's problem, really. So that's the evolutionary path of the sun into a red giant star. What happens next? So obviously, helium burning into carbon and oxygen likewise can't happen forever. Eventually, you get to a point where even the helium starts running out in the core because you've turned it all into carbon and oxygen. Well, at that point, there's no further fusion reactions that can happen in a star that's the size of the sun. So at this point, fusion switches off. You've done all the fusion you possibly can do, and the outer layers of the sun, the envelope that surrounds the sun, would drift off into space, actually be pushed off by very strong stellar winds into space. It would form a very beautiful sort of halo-shaped nebula called a planetary nebula, which would be sort of gently glowing. In the middle, you would have the leftover core of the sun. And the leftover core of the sun, no longer producing any energy through fusion, but still very, very hot initially, is called the white dwarf. And the white dwarfs appear on the Hertzsprung-Russell diagram down here, okay, below and to the left of the main sequence. Now, because they're down here, that's telling you that they're very small objects, because they're very hot, they have quite a high temperature, and yet they're not producing a lot of energy overall. So again, Stefan's law will tell you that they must have a very small surface area. They're not producing very much energy. So the white dwarfs all lie down here. So what a white dwarf is the collapsed core of a star like the sun. At the end of its life, the outer layers of the sun have drifted off into space, and you're left with a core that will contain a lot of carbon and oxygen. And that core is incredibly hot. It will compress into a very compressed state, but it'll still be made of atoms. The electrons that are mixed in there will stop it from collapsing further. It's called electron degeneracy pressure. Electrons don't like to occupy the same space, so they push out on each other, and it will stop the star from collapsing any further. And you will get a white dwarf. So just an ember really of the core of the original star. That white dwarf will carry on radiating energy into space. It'll cool down for the next trillion, 2 trillion, 10 trillion years. We don't know for sure. It'll take a long time to cool down, and eventually it will sort of cool down along this path here. Okay, so that's the evolutionary path of the sun. Then it will be on the main sequence for a couple of billion years yet, and then it'll evolve off and become a red giant. Outer layers will sort of drift off into space, and then you'll have the exposed core, which will cool down as a white dwarf. And you'd be expected really to plot that evolutionary path on a Hertzsprung-Russell diagram. Okay, so that's the sun. Now, there is a difference if you have a very high mass star. Low mass stars like the sun will follow a path like this. But if you've got a high mass star, a star that's up here, it doesn't actually turn into a red giant. It actually turns into a supergiant star. Now, what happens with the high mass stars, and it all happens very quickly. I say quickly, it happens in a few million years rather than a few billion years. With a high mass star, it runs out of its hydrogen very quickly, starts burning helium into carbon and oxygen in its core, but then very quickly the helium runs out, and at that point, unlike the sun, the carbon and oxygen can start fusing, and that starts fusing into the next heavier elements. And then they start fusing into the next heavy element. So you keep going through a sequence of the core stopping fusion because it's running out of its fuel, collapsing, getting hotter and denser, and then switching on the next fusion reaction. And it'll produce shells in the core of gradually heavier and heavier elements. So the heavier elements towards the middle of the core. Now, the problem with this is it can't go on forever because eventually you get to producing the element of iron in the core. Now, remember our diagram of binding energy per nucleon against mass number for isotopes. And if you remember that sort of hump-shaped graph, and iron, which has a mass number around about 55, 56, atomic number about 26, iron was the most stable element, so it had the highest binding energy per nucleon. Now, what that meant is you couldn't fuse iron and produce energy. So the problem is when you start making iron in the core of the star, which is exactly what's happening up here, when you start doing that, you can no longer produce energy through fusion to push the core of the star outwards and keep it in hydrostatic equilibrium, basically stop it from collapsing. So you produce iron, the star's doomed. Okay, it makes an iron core within a very short amount of time, and I think we're talking about days really of this happening. The entire star will collapse because the core of the star can't produce any energy to push outwards on the outlying layers that are all trying to push inwards because of gravity. So the entire star collapses onto the core. It collapses onto the core and then it rebounds in an enormous shock wave. A huge amount of energy gets released at this point. It's called a supernova explosion. And within a couple of weeks, a supernova can produce as much energy as a star like the sun can in its entire lifetime. In fact, a supernova can outshine an entire galaxy of billions of stars for a couple of weeks. So these stars up here, these real heavyweights, they'll evolve onto the supergiant branch, and very quickly they will explode as supernovas and disappear. Okay, they'll blow themselves to bits, or almost disappear. Okay, there is the last bit of what I'm going to talk about today is what happens after a supernova explosion. So I'll just put this down for a minute. So we talked about how a star like the sun ends its life as a white dwarf. What about a high mass star, something that's more than about 5 times the mass of the sun? So as we said, it will end up producing an iron core, and an iron core can't produce any energy through fusion. The iron core collapses, the whole star collapses onto the iron core, and then it rebounds in a shock wave, which is a supernova explosion. So, what happens next? Is there life after death for these stars that blow themselves apart? Well, for one thing, one thing that does happen in these explosions, which is quite interesting, is when the outer layers fall onto the core, the pressures and temperatures that get reached within the shock wave actually allow elements heavier than iron to be fused. You can fuse elements heavier than iron, but of course you have to put energy in rather than getting energy out. That happens when a star's collapsing because you've got energy coming in from gravitational potential energy as the star collapses. So you can fuse elements heavier than iron during a supernova explosion. And because of that, you get all the elements up to lead and uranium. You get all the rest of the periodic table, including things like tin and gold and so on. In fact, a lot of the elements that we need for life are actually formed inside a supernova explosion. And these elements will get then thrown across the universe from these huge explosions. And they will go into forming the next generation of stars. So the whole thing is circular. It's cyclical. As these stars die, their remains are thrown into the universe and then form the next generation of stars. So originally after the Big Bang, there was only really hydrogen and helium in the universe. If you look at the sun's 99% hydrogen and helium, but it's about 1% heavier elements than helium, elements that in astronomy we call metals. Anything heavier than helium is a metal. So the sun is about 1% metals. And why is that important? Because these heavier elements can form planets, and they also form a role in biological life. So, there's the old song, isn't there, "We are stardust." It's actually true. We're essentially the nuclear waste that's produced in a supernova explosion, at least most of the elements, or many of the elements in our body. Okay, so that's one thing that's produced by a supernova explosion, is the outer layers can fuse and form really heavy elements and get thrown into the universe. What about the core of the star? This core that collapsed, can that survive a supernova explosion? Well, interestingly enough, for some supernova explosions, we believe it can survive. And it can survive in a very, very exotic state. The core of the star will compress, and it will compress to the point at which electrons can no longer keep the star from collapsing further. So the electron degeneracy pressure that stops a white dwarf from collapsing doesn't work for these massive stars. The core of the star will collapse further. The limit on that is about 1.4 times the mass of the sun. It's called the Chandrasekhar limit. So if the core of the star is more than 1.4 times the mass of the sun, it will not stop at a white dwarf. It will carry on collapsing still further. And it will collapse so much that the protons and electrons that are within it will, through the weak interaction, will merge to form neutrons and neutrinos. The neutrinos fly off, and you're left with neutrons. You end up with a star that's held together by neutron degeneracy pressure. Essentially, you have the strong nuclear force and gravity in balance in these stars. And that happens at an incredibly high density, similar density to the nucleus of an atom. And these neutron stars have a very tiny radius. They're only about 10 or 20 kilometers across. Compared to a white dwarf that's about the size of the Earth, these things are about the size of a city. So very, very dense, incredibly dense. They're also spinning very rapidly, usually when they're born, because of conservation of angular momentum. We often see them as pulsars because as they spin, they capture charged particles in their magnetic fields and then fling them out in jets that spiral around in a sort of regular pattern, sometimes sweep past us a bit like a lighthouse. and we see these things in various different wavelengths flashing on and off as pulsars, sometimes over 100 times a second. They're spinning so fast. So these neutron stars, incredibly exotic objects. You get them from a really, really massive star. Even more massive stars, when they explode as a supernova, the cores can carry on collapsing beyond the point of a neutron star. And in fact, they can collapse so much that they reach a point where they're so dense that even light cannot escape its gravitational field. And at that point, they become a black hole. So a black hole is an object that's so dense that not even light can escape from its gravity. And we know that black holes do exist because we can detect them. Some black holes orbit other stars, and you can detect the gas from another star being pulled off and falling into the black hole and heating up and producing X-rays before it vanishes into the black hole. There is a little bit of physics that you do need to learn with black holes. One is working out its radius, called the Schwarzschild radius. So there is a formula for that you do need to learn and do a little calculation on, but that will be in the notes. Okay, the event horizon of a black hole is the point at which the escape velocity is greater than the speed of light, and that gives you, if you like, the radius of a black hole, the event horizon. That's not the size of the singularity in the middle, which in theory is zero. There's a point in the middle of infinite density where all the mass is contained. But you can work out the radius at which light can't escape. So that's basically it. That's the formation, the evolution of stars, and the Hertzsprung-Russell diagram. And that will conclude the section that we're going to be doing on stars. And the next bit will be galaxies and the Big Bang Theory. Okay, thank you for that.